share. Okay. Part 2, right? Okay. So this is a very exciting topic actually. So I hope that you guys can I hope you guys enjoyed Yonghyun's presentation yesterday. This is more like a explanation of what's going on behind this problem. So, okay, did I record? I recorded, right? Okay. So, so calibration weighting. So remember the regression weighting, right? This is our understanding of the regression estimator. So you can view the regression estimation as a pure optimization problem with a constraint. So the constraint is the calibration constraint. And so this is the very typical calibration constraint, and we want to find the unique one, right? You want to. This is there are so many omegas satisfying equation one, and we want to choose a single one, single weight, and one possible way is to choose. So once you choose a objective function or optimization function, then this is you can get a unique solution. Okay. And then the solution is indeed what? Indeed something like, right? So solution is indeed linear in X. So that means if you write a graph of the omega I on xi, it'll be linear, right? So it'll be a linear function. So that means what? If your x is somewhat, extreme, suppose you have something like this or some very extreme. So most of the weights will be distributed in something like that, right? But there may be some extreme values, and then extreme values may create the extreme weight, right? And the extreme weight can be either extremely large or extremely small up to the point of having negative values, right? And then the negative weight is not really pleasant, right? Because we spend money to collect data, and then if we put zero weight, then basically means what? We throw it away, right? It's basically wasting our money. If we put negative weight, we are doing actually make it worse, right? Whoever he says yes, we treat it as no, opposite way, right? That's a little bit very weird, decision. So we want to avoid negative way. So any practical, survey or whatever your project never have negative weights. So this is a kind of interesting problem, and survey sampling we addressed this problem a long time ago, but in the causal inference they kind of catch up, and then by Mueller, for example, consider this problem using the this objective function. So so this is a non-negative. So let's what is the G prime? Is you can see that omega plus omega 1 over omega, right? And minus omega. So cancels. And then so G prime omega equal to 0 at omega equal to 1. So that means it is indeed convex function with a minimum value at omega equal to 1. And also at omega equal to 1, this is 1, right? If we put 1 here, then the value minus, so this is actually at omega equal to, so G1 is 0. So this is actually nice because we know that it is a minimum at 1, but the minimum value is 0, right? So that means you can actually view it as a kind of something like this. I mean, it doesn't really have a quadratic form, but anyway, at least we know that this is non-negative. So we can view it as a more like a distance, some kind of distance. So actually you can view it as a distance from 1, right? The distance from 1. Okay. And also if you so G2 prime omega is what? 1 over omega. Okay. So that means in this range, actually you cannot really have a 0. So in this range between 0 and 1, 0 and infinity, this value will be positive. So that means this is a convex, strictly convex. So tangent, right? The tangent function, the change of tangent is positive, right? So, oops, the change of and nice thing about this approach is that the objective function here cannot take negative values, right? So then that means if the solution exists, then it should be the answer should be positive way. So this objective function exclude negative values. Okay, so that is so we use the same constraint. So so this constraint is just from the model whatever, right? I mean, so this constraint is given, but we want to consider different choices of the objective function, and one choice is this entropy function. Okay, so how to solve this? Well, we'll use a Lagrange multiplier, right? So we use Lagrange multiplier. So that means we have a objective function, and this is constraint. Okay. And remember, I use red color intentionally to emphasize that it is unknown parameter. Okay, so here the parameter is omega, and also another parameter is a lambda to be determined. Other things like black one, we observe. Okay, so Ti observe, Xi we observe, right? So we want to solve this, and the usual approach is to take the partial derivative. So partial derivative, okay, and then so then you know omega we if you do that, then we get this one, and then G is small g is a partial derivative. First of the partial derivative. Okay, we solve this, and then from here we can get this one, right? So G inverse. Okay, but what is a small g actually? What is a G omega? We already studied it here, right? G omega is log omega. So then that means the inverse of a log function is the exponential function, right? So that's why we get this one. So the derivation here from here to here is for general G. It actually is true for any G, but this one is only for the particular loss function in 2, which is the you know this entropy function. Okay. Now once you obtain the form, right? You now this omega becomes a black color, not a red color. That means what? That means I can compute the omega if I know lambda. right? But lambda is unknown. Okay. So lambda has to be solved, and then approach is we can how to solve it? Well, we can actually, since I know I have this one, I can just plug in to here. Okay, so plug in. Okay, that is sometimes called the profile. So you plug in, and then so that's why so this is original Lagrange multiplier, right? This is the function, and now I plug in omega hat lambda. Okay, and then once I plug in this guy here, right? Then now this function is a function of lambda only. Function of lambda only. And then, so this is, I have a plugin. So now I profile out omega. So originally I have two parameters. One is the omega, the other one is lambda. But I profile out omega and only express it in terms of lambda. So that's basically what we did here. And then what is G? Capital G. Well, G omega is omega log omega minus omega plus 1, right? So we know that. So we apply this function. Okay. So that's basically this one. So I should write it plus 1 here, but that's just constant. So it doesn't make any difference. So that's the first part. And the second part, so this guy is same lambda, right? And then we have this is omega. Okay, so I simply express. So this is a general, right? General expression, and then second equation is for the particular omega hat that we use to derive from the entropy function. So then nice thing about this, once you do that, turns out that you have some very nice simplification, which is this guy cancels with this guy. Okay, right? This guy, so we have a 1, 2, 3, 4 terms, but first and third term cancels to each other. And we only get, so, and then the only thing left with is this guy. Right? This guy, okay? Okay. And then this is the kind of objective function we want to optimize, right? So then we want to, if you take the partial derivative, right, with respect to lambda, then what? Then exponential term can go out, right? Inside the exponential, if you take the derivative with respect to lambda, then xi can go outside. So which is this one? Which actually, so this one is just the x bar, right? So this is actually set it to 0 becomes a calibration equation, right? Okay. So okay, that's nice, because here's basically what we did is we originally tried to use the Lagrange multiplier method, right? But from that we obtained the form of the wave function in terms of lambda, and then we compute. So the problem reduced to estimating parameter lambda, and lambda can be solved from maximizing this quantity. Okay. So so it turns out that is exactly dual problem. So that's actually so the primer problem was, in the primer problem parameter was omega. Okay. In the dual problem parameter is lambda. Okay. So, so to your problem, we maximize this, right? And then I'm gonna introduce the very details of the computation, because even if you understand everything, right? If you cannot really compute it, what's the point? So really important to have a good computational skill, especially for this convex optimization. I think maybe 30% or 40% of the statistical problem has actually a convex optimization component in it. So it's really a must must know-how topic that you need to master. And so here's using, so let's suppose I'm interested in maximizing this guy, right? So that's the goal. I want to find the maximizer of this quantity, which is a very nice one, but actually there's some subtle issues. So let's first decompose X into one and others. Okay, so you have because we know that one should be included, so let's separate out. So then we can write it as a lambda 0 plus lambda 1 x1. And then you can write, right? You can express it as something like this. Lambda 0 and so, okay. And then now let's take a look at what is the first, derivative with respect to lambda 0. That is actually, so this is easy problem, right? This is, you can get this one. So which or basically gives you some normalization constraint. Okay. So your intercept, lambda 0 is more like kind of intercept, right? So that becomes something like this. So that basically means try to make your weight to be add up to 1, essentially. So your weight should be add up to 1, right? So that's why we have this relationship. And then if you write, and then if you take the partial with respect to lambda 1, then this is actually becomes this one. Because we use this one. Okay, you just take the partial derivative with respect to lambda 0 first, and then lambda 1. Then you obtain this one. So that means what? This is kind of external mean, right? This is a weighted mean in the treatment group. And you want to find the weight, which is the weight is actually a kind of exponential function. And then we want to find a lambda that satisfies. Okay. How to actually solve this? So basically, why we are doing this? Well, because here this equation contains lambda 1 only, no lambda 0, right? So you actually have separate out. So this guy is equation for nonlinear equation for lambda 1, and then lambda 0 is automatically determined from equation 4, right? So you don't have to worry about lambda 0. So this is, so you now how to solve this, right? So turns out, okay, so so this one, if you this is actually nonlinear equation essentially, right? How to solve this? Well, usually this is more like this. Plus minus u inverse u. So basically this is partial derivative, and then you start with the initial value, and then so this, if you do Taylor expansion, then you can get it. This is a Newton method, right? Newton's method. But one thing we should so that is basically this what's going on here. So this particular weight, it has a very interesting expression. So you basically compute the kind of weighted variance and weighted mean, but you can get gamma. So what's going on? Well, it turns out that if you simply use this one, your Newton update does not necessarily increase. So you want to maximize, right? So you want to maximize, you want to find the maximizer. But if you so something like this. So this is suppose your Q is this, but you somehow you start with here, and then you kind of do something like this, right? I mean, that is the Newton-Raphson. So you want to, so this iteration usually have this find the solution and then eventually find this. But suppose the mountain is more like this, then you actually, if you do it, you could go down. So we want to make sure. So that means you went too far. So you want to, so here. So this is the basically the checking. So you have an update from 6, and then check whether your update indeed increase the Q function. Otherwise, your update is your step is too big. Okay, so you want to make your step half narrower. So that is basically the idea. So so if yes, is accepted. Otherwise, you narrow your step and compute and see whether you are doing so this is to make sure that you increase the Q2 function. You solve the optimization problem. Okay. So that is basically the idea for this convex optimization. Okay. So the primary problem, which is the constraint optimization problem, can be solved by its dual problem, which is the unconstrained optimization problem. So primary problem is about omega, and dual problem is about lambda, right? And the primary problem is an n1 dimensional optimization problem, while the dual problem is a p dimensional optimization problem. The dual problem is numerically more stable, right? I mean, so this is easier to solve than solving the original problem, optimization problem. Okay. So I hope that makes sense to you. And here's a generalization. So this is a very maybe a little bit difficult, but hopefully it's useful. Okay. So the derivation here is for particular choice of the G function, right? Entropy G function. Now, if you remember Yonghyun's talk yesterday, he kind of used the generalized entropy, right? So we want to do the same thing, and then what is the core part of the optimization problem? So the structure of the dual problem is the same. I mean, the primal problem is the same. We minimize Q1, right, which is characterized by G. G is a convex function subject to linear constraint. And then this one, for how to solve this one, let's use Lagrange multiplier, right? So if you use Lagrange multiplier, then we know that the solution should be of this form 3. So this part, right? G inverse x prime lambda hat. I mean, G prime X prime lambda. This solution itself is true for any G, any convex G. Okay. That's good. So that this part is okay. And now, what did we do after that? When we plug in, right? We plug in and profile out. So we want to do the same thing. So you plug in, right? Plug in and profile out and write it as a function of lambda. Then you have this, right? Okay. So that we can call it profile loss function. And then here's the really key idea is that this guy, you now view it as a function of lambda. Okay. And it's so important that it has a name. The name is convex conjugate or Legendre transformation. So what is the Legendre transformation? I will explain a little bit, but it's actually the key part of the dual expression of the function optimization. Okay. So this is a definition. Okay. So this is here's two things. This is a definition, right? So this is called convex conjugate or Legendre transformation. So that's one part. And I will explain in the next page. Second part we need to check is that whether we have this equality, right? We haven't shown. So we need to check. So the second part, let's check the second part. Okay. So this part is no problem, right? We already have this, right? We already, obtained this using the Lagrange multiplier. But what we haven't really clarified is whether we can write it as a low lambda x. So this part is same, right? So this part is this part. The first part is that so we have a 1, 2, 3, right? So then 1 plus 2. So 1 plus 2 becomes this. Okay. Well, turns out that if you just use the definition, right? Then what is this? That is minus, let's write the second term first. G prime lambda prime xi plus lambda prime G inverse, lambda prime xi, and then G inverse lambda prime xi, right? This is nothing but, rewriting rho over lambda prime x using the definition of rho, right? And then if you view it, and then we want to take the summation, right? So if you look at this, what is the summation of this guy, right? Of this guy. By the way, let me back up. I better. So actually one thing we should note is that this guy is omega I hat lambda. This guy, right? So this guy is omega hat lambda. So we are done actually, right? Because capital G of omega hat lambda is this guy. Sure. So
And it's like what?
which condition?
It's like
Ah, so G prime.
yeah, but it's fun.
I see. We don't need that. We are not really using this book.
All just like this.
But it's that's a good question. So yeah. So deriving. So question was. Which page is it?
Ten.
Okay. So any convex. So why do we need it? Actually, we don't use this condition. But this guy actually is indeed G1 equal to 0, right? So that means actually it means G inverse 0 equal to 1, right? That means omega I hat lambda equal to 0 is 1. Okay. So we want to, so that means if there's no constraint, okay, then so if there's no constraint, no calibration constraint, then we want the solution to be equal to 1, equal weight, right? So that is kind of this condition. Yeah, that's a very good question. uh, let's continue. And then another implication is that if sample size is really large, then calibration condition will be satisfied, right? I mean, so that means your weight, calibration weight, should close to be equal weight, end of the day. So that's the reason. Okay. Now, the final weight. So that I explained this, right? I mean, so this equivalence. So the algebraic equivalence is been shown, and I haven't really explained the meaning of the complex conjugate yet. But before do that, let's check the second blend. So final weight, right? Final, we already showed this. But what I like to show is the equivalence between the two. So final weight, basically the equality here is an expression in terms of the original G, right? Original convex function. While the expression here is, so the equality, second equality is the expression in terms of the dual function, I mean the conjugate function. So, right? So the wave function can be understood as a inverse of the partial derivative of G, or partial derivative of the convex conjugate function. And now let's try to see why this is true. Well, let's using the definition, right? What is the what is the prime partial derivative? First of the partial derivative of rho. Well, so it's a function product, right? G times, I mean, nu times G inverse nu. So that is G inverse nu plus nu times G inverse nu prime minus G of G inverse nu times G prime G inverse nu prime. Okay, so I just this is a kind of function, right? Function. I just apply the differentiation, and the differentiation will be this form. Will have this one. And now this guy is what? Is equal to nu. G over G inverse. Nu is nu, right? So and so that means you can actually have a cancellation. Cancellation. So that means you can get rho prime nu is equal to G inverse nu. So that is the result. Okay. So what is the meaning of the Legendre transformation? I should have used this space. Well, it's a little bit intriguing concept. So idea is, okay, I want to express given function, right? So f is a function. So given function, I want to find a different way of understanding this function. One way, so how I understand this function? Well, you could use plot, right? So Cartesian plot. You can use x and y, and then plot it. For each point, you plot y value, corresponding y value. Then you can understand the behavior of this function, right? So that's we know. That's what we used to know. It's like but here's a very intriguing idea. The idea is, okay, rather than using a set of x and y point, we can use a set of tangent lines specify their slope and intercept. Okay, so this is a slope tangent, and this is a kind of intercept. So basically, idea is, okay, for each point you can kind of so yeah, it's a little bit. So idea is, okay, how can I understand this? Well, given the p, okay, given p, so suppose p is a particular slope, and then there should be a point that gives this p as a slope. Okay, and then this difference is actually intercept, corresponds to intercept. So and then you can actually change the slope, and then you can get different intercept. So then the pair of the slope and intercept characterize the original function. So that's very kind of a intriguing idea. So this is the definition of the dual. I mean conjugate dual. I mean Legendre transformation, or convex conjugate function. Okay, and then what do I mean by that? So as a maximizer, so you want to find, so given p, right? Given p, you want to first identify the point at which this point is maximized. Okay, the point is this one, right? Because you wanna solve this. You wanna solve this. So the point is this. And then you evaluate this difference. So this is actually what? This is original function. This is a linear function without a slope. So the difference will be slope. Okay. A difference will be intercept. Sorry, so, y-intercept. Okay. Okay. So anyway, so basically, you you don't have to understand everything, but the only part this is just how we get this definition. So this definition actually comes from here by choosing f equal g. Okay, because what? Because you actually have a, so you given, so this, so okay, rho nu, right, is, so p is nu, so nu times what is x? X is f prime, which is a g inverse nu minus g of g inverse nu, right? So because here is, we can, we use the nu, right? We use the f is actually g. Then the evaluating this guy at here corresponds to writing this. Okay, it's very intriguing, but it is true. So because you want to write it as a function of p, which is as a function of nu, and then you play with partial derivative of capital G, which is the small g, and then you use actually the inverse function of it. Okay. So okay. Anyway, that is conjugate, convex conjugate, and this is a typical tabulation. Is an examples of the convex conjugate. So so you can check that if you take the partial differentiation, right? So if you take the differentiation, you get this wave function. Okay. Or you compute the differentiation, right? And then compute the inverse. Then you can get this one too. So two ways of obtaining weight, right? One is using G. Another way is using rho. Okay. So that is basically the idea. I think this is a little bit too much for 521, but hopefully it will be helpful for your study, for your research. And this is even more too much because we are talking about now, we want to talk about statistical property. Okay. So yeah, so suppose I'm interested in estimating the mean of y0, right? Y1, okay. And I already, I use the generalized entropy, right, to obtain the final weight, final calibration weight, and the final calibration weight has a Lagrange multiplier parameter lambda hat, which satisfy this. Okay, so this really a typical problem, right? But I like to. So if I know G, right? If I know a particular function like this, then I know how to do differentiation and everything. But this is a little bit more difficult because we want to derive a theory for general G. Okay. So first thing is to we separate out, and so when it comes to do deriving the theory, the tricky part is that in order, this is the theta is a parameter of interest, but to estimate the theta, we estimate another parameter. Here, we estimated lambda. Okay, we estimated lambda. And lambda is a kind of a nuisance parameter. Sometimes we call it nuisance parameter. In the sense that we need to estimate it in order to estimate parameter of interest. Okay. So in that sense, this is actually a kind of something like this. It's a function of lambda hat, the parameter. My estimator is a function of an estimated nuisance parameter. And then what you want to do is to take the linearization, apply linearization for the implicit parameter, nuisance parameter lambda. And then means we need to first understand what is the probability limit. So what is the limit where this lambda hat goes to? That in order to apply Taylor expansion, we need to understand what it converges to. Turns out that, so let's call this a limit. Okay. So we don't have to know, we cannot really know the specific form of the lambda star limit because we start with the general G. But one thing we know is that it satisfies the equation. So the key idea is that, okay, the catch is that we write this guy is actually estimating equation for lambda. You can view it as this, okay? So if you write it this way, okay, and then that's kind of almost equivalent to so this is the equation for lambda, right? This is the estimated equation for lambda. But the limit should satisfy the expectation of lambda, expectation of u evaluated at the limit. And then so now the question is, what is this? What is the expectation? Well, you have this one, right? So this in this particular case, this is actually nothing but G inverse lambda hat xi prime xi minus x bar, right? So this is u. This is u lambda hat. And I know that this is a kind of simple sampling. And so the limit, if you take the expectation, so here the expectation is with respect to t sampling, with respect to sampling. So it's the expectation with sampling means that we kind of equal. So end of the day we'll have something like, so I guess let's do it more rigorous. Okay, so expectation, take expectation, we get n1 over n, right? And then G inverse lambda star, the limit 0 plus lambda star x1 I times xi minus x bar. Sorry for the mess. Okay. And so we know this should be 0. So in order for this to be 0, that means this guy has to be 1 over n1. So that means lambda 1 star should be 0. So this guy should be, because we don't want this to be dependent on I. So we want to remove the dependence on I, individual. So that means this guy should be 0 in order to remove the dependence of the x1, I. And then this guy, so that's why we get this. Okay. So this is a little bit, so to show this rigorously is a little bit involved, but the big picture is that we need this condition. After that, we can write the calibration estimator as this. This is actually 0. So because this is 0, we can just multiply anything. And then take the partial derivative with respect to lambda, solve this to find the beta star, which gives the linearization. But this is a little bit too much, maybe. I will, yeah, so probably I will explain next week further, but this is probably too much, but actually it turns out to be very useful in the research. So, okay, I think that's all for today. And see you next week.